What's up, pre-calculus students? Mr. Mester coming at you with the 6-2 homework video where we introduce radians. Radians is a distance around a circle. It is not an arbitrary number like 360 degrees. If you watch the video in my class about why there are 360 degrees, there's a couple reasons, but it's not just like a number that would be used universally. Like aliens probably wouldn't use 360 degrees around a circle. They'd probably use 2 pi radians, which is a distance around a circle with a radius 1. 360 is very close to the amount of days in the year. 360 is very divisible by a lot of numbers. So that's where human beings kind of came up with the idea of 360s and circles. Year is about 360. And then boom, divide 360 by so many different numbers. It just kind of makes sense, but it's very much a human made up number. Now we are talking about angles in a different way than we're used to. We're going to be talking about angles like in a coordinate plane. So we're talking about standard position, where the angle of 0, you have your initial ray on the x-axis going to the right. And this is kind of where your angles start. This would be like an angle of 0. And you would add angles going around counterclockwise. It's almost like you're looking into the horizon. That's 0. And then if you look up, where should I go? I should go this way. If you look up, we're adding angles. And if we keep going around, this is adding angles. And if we look down, we'd be subtracting angles. And clockwise would be subtracting angles. So going around our circle this way, I'd continue to go counterclockwise to get around our circle to get what you consider 360 degrees. But we know that's equivalent to 2 pi radians. Why? Because we are talking about a length, an arc length, or a circumference around a circle with a radius of 1. Okay, if you calculate the circumference of a circle with a radius of 1, circumference formula is 2 times pi times r. The circumference of a circle with radius 1 is 2 pi. So we say this arc length of this unit circle, and let's just get this in mind now. The circumference is 2 pi. Okay, so we say 2 pi radians is equivalent to 360 degrees. Divide this by 2. You get pi is equal to 180 degrees. So halfway around this circle, this arc length would be pi. Divide this by 2. Pi divided by 2 is just pi over 2. 180 divided by 2 is 90. So pi over 2 is equivalent to 90 degrees. So what we think about of a 90-degree angle is an arc length of a circle radius 1 of pi over 2 radians. My cursor just froze. We're going to keep like degrees in our brains. It will help us when kind of doing calculations, but mostly like the degrees we're going to keep in our brains are like 30 degrees, 60 degrees. 30 degrees being a smaller angle, 60 degrees being a larger angle, 45 smack dab in between the two. Where the heck is my cursor? So anyways, this one is going to be 90 degrees. If I took pi and divided by 3, 180 divided by 3 is 60. Pi divided by 3 is pi over 3, so there'd be 60 degrees here. Take pi and divide it by 4. You get pi over 4. There we go. So 180 divided by 2. 90 degrees is equivalent to arc length of pi over 2 and a circle radius 1. Or pi over 2 radians. Pi over 3, take 180 and divide it by 3, I get 60. Take 180 and divide it by 4, might not be obvious, but it's 45 degrees if you do that calculation. Or take pi over 2 and multiply it by a half. Take 90 and multiply it by a half. Maybe that's an easier way to do that. So maybe let's go into 90 degrees times a half. That's 45 degrees. Probably easy enough to do pi and divided by 6. 180 degrees divided by 6 is going to be 30 degrees. And you could also do pi over 2 and times a third. 90 divided by 30. Okay, cool. So we are not using degrees. They're going to be in the background in our brains, but we will be forced to kind of understand radian locations. Now, it's going to be easy to do so long as you understand adding and subtracting angles and the direction of things. What I recommend students do, and this is important because you're going to be forced to find where is this radian measurement located and what is the reference angle that is created when you are located at this radian measurement. What I recommend doing, and you probably don't need the circle, but I'm going to provide the circle anyways, is just kind of keep things to some like standard base radians that you know, where like this is 0, this is pi, all the way around our circle is 2 pi. And kind of like use these to your advantage. So if I ask you to find 7 pi over 6, what is that? Well, I know that 6 pi over 6 is the same as pi, and 6 pi over 6 plus pi over 6 would be 7 pi's over 6. Now, watch how I can find this location. I have pi, which is equivalent to 6 pi over 6. I understand that adding is going around counterclockwise, subtracting will be going around clockwise. I will take 6 pi over 6, I will add pi over 6, which means I will go like counterclockwise by pi over 6. What's pi over 6? You're going to keep this in your brain. Think about this fraction, pi divided by 6. Dividing by a bigger number creates a smaller value. So pi divided by 6 is going to be a smaller angle. It's going to be our 30-degree angle versus pi over 3, which will divided be a larger number than pi over 6. That'll create a bigger angle. That'll be our 6-degree angle. You got to remember that our pi over 6s create 30-degree reference angles. So 6 pi over 6 plus pi over 6 puts you right here. This would be the location of 7 pi over 6. There's 7 pi over 6. It is a 30-degree reference, and the arc length from 0 around this unit circle would be 7 pi over 6 radians. What about 2 pi over 3? Well, I know 3 pi over 3, which is pi minus a pi over 3, is equivalent to 2 pi's over 3. I know that pi over 3 dividing by 3 is going to create a larger value than dividing by 6. Pi over 3 creates 60-degree angles, which we kind of did up here. Pi over 3 is equivalent to 60-degree angles. To find where 2 pi over 3 is, we will go to pi, 3 pi over 3. We will then subtract a pi over 3. We will subtract 60 degrees, and we will be located in the second quadrant. And the angle that is created with this x-axis is 60 degrees. And this is how we find the location of these radian measurements. I'll do a couple more on this. 11 pi over 6, I know it's close to 12 pi over 6. That's the same as 2 pi minus a pi over 6. Well, around my circle, 2 pi, subtract pi over 6 is like subtracting 30 degrees, gives me this location. This location creates a reference angle with the x-axis of 30 degrees. We like to talk about reference angles and to keep that angle measurement of 30, 60, and 45 for very good reasons, because we know like our triangles, 30, 60, 90, and 45, 45, 90, we will be using that in this lesson. But boom, this would be the location 11 pi over 6. This is the location 2 pi over 3. Cool, 3 pi over 4 is very close to 4 pi over 4, subtracting a pi over 4. 4 pi over 4 is the same as pi. Pi over 4 is equivalent to 45 degrees. So I will go over to 4 pi over 4. I will subtract 45 degrees or subtract pi over 4 radians, and I get this location, second quadrant, reference angle, 45 degrees. We're going to be doing this more in the next. So 5 pi over 3, I'd say it's 6 pi over 3 minus a pi over 3. Around the circle, subtract 60 degrees. Seven pi over 4. 8 pi over 4 minus pi over 4. Go around the circle, subtract 45 degrees. 4 pi over 3. 3 pi over 3 plus pi over 3. 3 pi over 3 is the same as pi. 3 pi over 3 plus 60 degrees. Boom, this is what we want you to do. 5 pi over 6, 6 pi over 6 minus pi over 6. So the key is to be able to write pi and 2 pi as amounts of pi's over whatever. So like 3 pi over 3 is pi, 6 pi over 6 is pi, 12 pi over 6 is 2 pi, 6 pi over 3 is 2 pi, 8 pi over 4 is 2 pi, and then add or subtract one of these pi over whatevers. So here, 6 pi over 6 minus pi over 6. Pi over 6 is equivalent to 30 degrees, and that would be the location. Okay, so it's like understanding adding and subtracting angles, understanding fractions and equivalent fractions to pi's and 2 pi's. Boom, useful for radian locations. And that's what we're going to do here. What we just kind of introduced there. I'll do it, but maybe I won't write out everything. I'm just going to go straight to where the angle is located, and I'm going to write the reference like degree measurement for myself. So pi over 6. I know pi divided by 6 is like 180 divided by 6, 30 degrees. We start here at 0, and we will go in a positive direction with angle measurements, keeping this in mind of counterclockwise versus clockwise. Boom, this is a 30-degree reference angle. This arc length would be pi over 6 if we're talking about a circle radius 1. But this is what we want you to do, is to write this terminal ray. We got our initial ray here on our x-axis. Our terminal ray is like the ray that would pass through the arc that's just pi over 6, like the end of the arc, if that makes sense. Pi over 3 would be 60 degrees. Again, you could take pi divided by 3. 180 degrees divided by 6, but divided by 3 is 60. Pi over 4, 45. Pi over 2, 90. Okay. Now, here comes the tougher ones, but it's not that tough if you just keep the idea in mind. I'll do it for the first couple, and then I'm just going to kind of like talk you through it, because you need to be able to do this like pretty quickly, eventually kind of do a lot of different steps when we're kind of combining trigonometry and radians in your brain, potentially. 4 pi over 3, I know is a pi over 3 away from 3 pi over 3. I will take 3 pi over 3, add a pi over 3. Three pi over 3, add a pi over 3. A pi over 3 is a 60-degree angle, so I'm here in the third quadrant, 60 degrees away from my x-axis. 3 pi over 4, I'll start with 4 pi over 4 and subtract a pi over 4. I will start with pi, which is 4 pi over 4. I will subtract a pi over 4. I'm 45 degrees away from the x-axis. I'm subtracting pi over 4. And I'm located here in the third quadrant, my terminal ray. So this would be the radian measurement, 3 pi over 4 radians. 5 pi over 6, 6 pi over 6 minus a pi over 6, 6 pi over 6 minus 30 degrees, pi over 6, creating the smaller angle measurement versus pi over 3 creating a larger, dividing by a bigger number creates a smaller value, dividing by a smaller number creates a larger value. So keep that in mind. If I'm dividing by 6, I'm going to get a 30-degree angle. If I divide by 3, I get a 60-degree angle. 11 pi over 6, 12 pi over 6 minus a pi over 6. I go all the way around my circle to 12 pi over 6, which is 2 pi. Adding, subtracting, subtract a pi over 6, subtract 30 degrees, and you're right there in the fourth quadrant, 30 degrees away from the x-axis. All right, now I'm just going to kind of walk through it. 3 pi over 3 minus pi over 3 gives you a 60-degree kind of reference angle in the second quadrant. 6 pi over 6 plus a pi over 6 creates this 30-degree reference angle in the third quadrant. 4 pi over 4 plus a pi over 4 creates a 45-degree reference angle in the third quadrant. Cursor is not liking me today. There it is. So there's a 45-degree reference angle. Pi, halfway around the circle. I'll just kind of show my terminal ray being there. I would probably say that the reference angle is 90 degrees, but like, we're good. You could say the reference angle is 0 if you wanted to. I don't want to say it's the reference angle of 90 degrees with the y-axis. We don't like to talk about the y-axis. We like to talk about reference to the x-axis. That's important. 7 pi over 4, 8 pi over 4 minus 8 pi over 4 puts me right there. Pi's over 4, 45 degrees equivalency. 0 to pi. Located at the same location, two different angles, an angle of 0. We don't have any angle at all. Angle of 360 degrees or 2 pi radians means we've gone around the circle entirely. Located in the same location, but different angles. 5 pi over 3, 6 pi over 3 minus a pi over 3 puts me there, 60 degrees away from the x-axis. 3 pi over 2, this is one we haven't really talked about, but if this is pi, add pi over 2. Pi over 2 being 90 degrees, adding pi over 2 puts me smack down here at 270 degrees. This is one we haven't really seen. Going the other way, what if I give you the reference angles? Could you give me the radians? Okay. Key guys, is those like standard first, I guess, standard acute angle equivalencies. What do I mean by that? Like, what radian measurement is equivalent to the acute angle of 30 degrees, 45 degrees, 60 degrees. You got to remember, and this is important, just like your special right triangles will be important later, and were important for our first lesson. Pi over 6 is equivalent to a 30-degree angle. Pi over 4 is equivalent to a 45-degree angle. Pi over 3 equivalent to a 60-degree angle. Okay? If I am showing you the reference angles, and I say, what is the radian measurement of the following angles in standard position, A, O, B? You're like, okay, it creates a 60-degree angle with the x-axis. 60-degree angles are pi over 3s. So this would just be pi over 3, 60 degrees. Now let's look at AOC. AOC creates a 30-degree reference with the x-axis. So like COD is 30 degrees. What is AOC? Well, how I would do this is say, well, I know that pi is 180 degrees. I know that pi over 6 is 30 degrees. I know that this direction, this clockwise direction, we are subtracting angles versus counterclockwise, we are adding. Counterclockwise, we're adding. Clockwise, we're subtracting. I can see I would go to pi and I would subtract pi over 6. I have 6 pi over 6 minus a pi over 6. You should be able to determine that AOC is a 5 pi over 6 radian measurement. AOD, halfway around the circle, pi radians. 2 pi, 360 degrees, divided by 2, pi, 180. AOE, 45-degree reference angle with the x-axis, 45 degrees more than pi, or than 180 degrees. So I'll take pi and I'll add pi over 4. I'll take 4 pi over 4, add a pi over 4, I get to the radian measurement of 5 pi over 4. AOF. You want to say it's pi over 2, but it's not. Two ways to do it. You can either say I get to pi and I add what is a 90-degree equivalency in terms of distances, in terms of radians. 90 degrees is pi over 2. So AOF could either be pi plus pi over 2 or pi plus, or you go all the way around your circle to 2 pi and subtract pi over 2. You could also, but we're not going to worry about that. We're going to talk about standard position angles being between 0 and 2 pi. You could actually go from 0 and subtract pi over 2. And we will talk about how negative pi over 2 radians is correct in terms of its location, but in terms of like standard position, we will be going around positively, and we won't want that answer. We'll either want 3 pi over 2 by adding from pi or 3 pi over 2 by subtracting from 2 pi. Okay. All right. What if my circle is a larger radius? Well, we talked about this in class, how like similar to triangles being proportional, circles are also proportional. So the proportionality is like our arc length divided by our circumference. These have to be equivalent with circles. Okay? They have to be proportional, so these ratios, arc length to circumference, have to be equal. Well, if I talk about our unit circle, we talk about the arc length of a unit circle being our radian measurement, and the circumference of our circle with a radius of 1 is 2 pi. Here, for a circle with a radius of r, where we don't know, like the radius could be different. The arc length is what we could find. I'll just call it L, and the circumference is 2 times pi times r. We get this that can be used or can be simplified to figure out that the arc length L, when you multiply both sides by 2 pi r, is just equivalent to the radian measurement times r. So the arc length of a bigger circle or smaller circle is equivalent to the radian measurement that you got, the arc length of your unit circle times the radius of your new circle. So like I'll show you two different ways, like whether you're just using the proportion just will work for all situations, or like you might be given the arc length of the big circle and then asked to find the radian measurement that it's equivalent to. All different things you can be asked, but two different ways. Measure arc X, Y, Z. We see our unit circle here, and we see our radian measurement, or our arc length of our unit circle is 4 pi over 3. So we can say like 4 pi over 3 is our radian measurement divided by 2 pi is equivalent to the arc length, X, Y, Z, over 2 times pi times the radius. You can see this location is 6, 0. So this radius of the larger circle is 6. Again, if you multiply both sides by 2 pi times 6, the 2 pi's will cancel, or my arc length is just equivalent to r times the radian measurement. 4 pi over 3 divided by 3 is 24 pi's over 3, or divide the top and bottom by 6, and you get 8. Divide the top and bottom by 3, and you get 8 pi. Okay? So that's the arc length XYZ. Find the measurement of the minor arc XZ. Okay, if this is 4 pi over 3 radians, we are covering a large portion of the circle. We're covering 180 plus 60. If you were to consider in standard position this measurement here, this creates a 60-degree reference angle. Imagine we're going around this way, and we're talking about a positive measurement. Well, there's two ways we can do this. I'll show you. Show you two different ways. And I'm sure you guys are thinking of two different ways. Use your brains to get this answer. We can tell that this is going to be 2 pi over 3 radians if we're talking about this being in like standard position. 2 pi over 3 plus 4 pi over 3 is 6 pi's over 3, which is 2 pi. So it's like we cover the rest of the circle. Maybe if this is 4 pi over 3, you keep going plus 2 pi over 3, and we get the rest of the circle. Maybe that's what you consider. Different ways to do it. So again, 2 pi over 3 over 2 pi has to be equivalent to the arc xz over the circumference of this larger circle, which is 12 pi, or 2 pi times 6. Multiply both sides by 2 pi times 6, or 12 pi. What you end up is the arc, the radian measurement, times the radius of 6, because the 2 pi's will cancel. If you multiply by 2 pi times 6, multiply by 2 pi times 6, the 2 pi's will cancel. The radian measurement times the radius of the big circle will give you your arc length. So 4 pi. Or the circumference of the big circle is 12 pi. So that's the total distance around the big circle. If I already went 8 pi, what's left? 4 pi. Many of you, I bet you could have figured this out yourself. Okay, now we start to connect trigonometry and radians, or angles inside circles. Okay, we start to connect our triangles and our circles. Here we have a circle. Okay, we see from this point right here that the circle has a radius of 1.3. We go over 1.3. Okay, this is very important. We also see a coordinate on your circle, and we place a like terminal ray that like connects the origin to this point. So we see this 0.5 comma 1.2. Well, what does that point mean? Well, the point is an x position and a y position. What we can do is think about this coordinate as distances. How this x coordinate 0.5 shows our distance, an x distance from our origin. The y coordinate 1.2 shows a y distance from an origin to that point. What have we just created? A right triangle inside a circle. And this is day 2. We're going to place angle measurements, radian measurements, and then from day 1, we're going to use our triangles, and we're going to kind of place our triangles inside the circle. Because if I ask you a trigonometry question, you're like, oh, I need triangles. I need SOHCAHTOA. SOHCAHTOA is not disappearing on you. And on the next page, we're going to talk about our special right triangles being placed inside our unit circle. Special right triangles with our radius of 1, our 30, 60, 90, 45, 45, 90, being placed inside our unit circle. We're not there yet because we're talking about a circle radius 1.3. It's not a unit circle yet, so we just have our x distance, our y distance, and our r distance. We talked about in unit 1. We're going to switch up our triangles from like a, b, and c to x, y, and r. Great. The sign of a is right here. Reference to a, opposite over hypotenuse, 1.2 over 1.3. I would want you to be able to write that as 12 over 13 by multiplying the top and bottom by 10. Cosine of a adjacent over hypotenuse. Tangent of A, opposite over adjacent. Secant is the reciprocal of cosine. I already found cosine, so just flip it, or it's hypotenuse over adjacent. Cotangent, reciprocal of tangent. So adjacent over opposite. Cosecant is the reciprocal function of sine. Flip the letters, flip the reciprocals, for reciprocals. So cosecant is not the reciprocal of cosine. Cosecant is the reciprocal of sine. And cosecant of A would be hypotenuse over opposite. So sine flipped. Cool. Good start. Triangles inside circles. Okay. We got a unit circle. Okay. We have a circle with a radius of 1. So this would be the point like 1, 0. We have the point 0.6, 0.8. So very similar to the last one where we're going over a little bit less than we're going up. What is, and this is angle AOB in standard position, terminal ray, OB, boom. Find the sine of AOB. It's like we don't know the angle, but since we know the radius and we know the x distance and the y distance, the x distance, 0.6, the y distance, 0.8, we have placed a triangle inside a circle, and this theta is angle AOB. We can find all of the trig functions of this angle measurement because we have just drawn a triangle inside our circle. So the sine, opposite over hypotenuse, is 0.8 over 1. What's great is whenever we have a unit circle, we're dividing by 1. So we don't have to worry about h necessarily. We just have the opposite over 1, the adjacent over 1. Dividing by 1 doesn't change it. So cosine, and maybe I'll just show it just to like really drive it home. When you're dividing by 1, nothing changes. Cosine, adjacent over 1. Tangent, opposite over adjacent. That's 8/6, which is 4/3. Secant, reciprocal of cosine. So this is 3/5. It's 6/10. 3/5. Secant would be 5/3. You could get that by also flipping things if you wanted to. But I'd probably want you to write it as 6/10, which is flipped to be 10/6, which is 5/3. Cosecant, this is 1 over 0.8, or 0.8 is 8/10. 8/10 is 4/5. So 5/4. Cotangent, 3/4. Oh, guess what? This is our 3, 4, 5 right triangle. Its equivalency shrunk into a unit circle. Remember, and lesson 1's key thing, similar triangles. Side lengths are proportional. That's why trigonometry is there. If you have any 3, 4, 5 oriented right triangle, here are the ratios you have to have. Now, combine special right triangles located inside circles to find the trig function of a radian measurement. This is the key, team. This is the key for the next day and the next day, and this is the key for the rest of the year in terms of learning new material, is being able to do this. So, what do we have to break out? My friend, the 30, 60, 90 triangle, and my friend, the 45, 45, 90 triangle. So, I'm going to just draw it right here. 30, 60, 90. Okay. 2 orientations of the 30, 60, 90. A tall 30, 60, 90, where the larger angle is this base angle. The other orientation is the short 30, 60, 90 triangle, where the base angle here is 30 degrees. It's the same triangle, just looks different. What are the side lengths? We have you do this and practice this. You got to know this. It's 1, 1/2, and root 3 over 2. 1/2 is less than root 3 over 2. Root 3 is bigger than 1. We know this. Square root of 1 is 1. Square root of 4 is 2. The square root of 3 is somewhere between 1 and 2. So square root of 3 over 2 is the longer side length. And then we have our 45, 45, 90 triangle. Bam, bam, bam. It's isosceles. The side lengths have to be the same, the leg lengths, and that length is root 2 over 2. That's got to be in your head as well. Okay? Okay. We got our unit circle. Ugh. I don't know why that's not there. But okay, we got our unit circle. Now, unlike the last two questions where you're going to have the coordinate, what we're going to do is place the triangle. We could then go to the coordinate, or you just keep the triangle. Let me show you what I mean. Pi over 6. All right, pi over 6 equivalent to 30 degrees. This is what we were just doing. You start at the angle 0. We go pi over 6 radians around my unit circle. Unit circle radius of 1, 30 degrees. Okay. What's this coordinate here? Well, like, don't worry about the coordinate, but like, what can you draw that we already know is this triangle? If you drop a y length down, we always want to go with the x-axis because those are the easy reference angles to produce. This is our y distance from our x-axis up. This is our x distance from our origin over. And boom, there's that triangle right there. Okay, this must be the longer length, root 3 over 2. This must be the shorter length, 1/2. This combines day 1 and day 2 and combines circles and radians with trigonometry and special right triangles. Boom. Now, if I ask you, what is the sine of pi over 6? You could do it. You have your triangle, the equivalent angle to the radian measurement. What is the ratio? Opposite over hypotenuse. Opposite is 1/2, hypotenuse is 1. Divide by 1. Done. Cosine. Adjacent over hypotenuse. The hypotenuse is 1. Done. Tangent. Opposite over adjacent. Simplify. Rationalize. Cosecant, reciprocal of sine. Secant, reciprocal of cosine. Or you could do hypotenuse over adjacent. 1 over root 3 over 2, which is 2 over root 3. Rationalized. Multiply the top and bottom by root 3. Cotangent, reciprocal of tangent. Don't flip this, flip this. Done. This is it, guys. This is actually the rest of the semester is this understanding. What you are going to get to is like not see anything, but I give you a question. What is the sine of pi over 6? And you'd be like, okay, pi over 6, 30 degrees, 30, 60, 90, short orientation, 1/2 vertical length divided by 1, 1/2. Don't gloss over this. This is the rest of the semester. We're doing more of this next class. We'll do more of this for the rest of the year. You have to understand this. You have to know your special right triangles, and then you have to be able to understand your radian locations. We are putting triangles inside of a unit circle. Pi over 4, 45 degrees. Oh, I know a 45, 45, 90 triangle with a radius of 1. Radians arc lengths of a triangle with a radius of 1. Pi over 4, starting at 0, 45 degrees reference with the x-axis, hypotenuse of 1. Oh, I know a 45, 45, 90 triangle like this. Instead of placing the xy coordinate, I can kind of understand this xy coordinate by dropping this down to the x-axis to have a y distance, popping this over to have an x distance. What are those distances? Root 2 over 2, because it's an isosceles right triangle. We've connected day 1 with day 2. Now, if I ask you what's the sine of pi over 4, you can give it to me. Root 2 over 2. Root 2 over 2. Opposite over adjacent, 1. Flip it. 2 over root 2, which is 2 root 2 over 2, which is root 2. Or if you think about it, when we first found these side lengths, we had that it was 1 over root 2. And then because we took the square root of a half to find the side lengths. And then we rationalize the square root of 1 over, we rationalize the square root of 1/2, or 1 over the square root of 2. Secant, tangent, cotangent. Let me just show you it. I'm sorry. I don't want you to be confused. Bam. Okay. Pi over 3. Oh, pi over 3 is equivalent to 60 degrees. All right, so starting at 0, going an arc length of pi over, well, I don't understand this. Going an arc length of pi over 3 around my unit circle creates this terminal ray, which creates a reference angle of 60 degrees, creates a tall 30, 60, 90 triangle with a hypotenuse of 1 because the radius of this circle is 1. Okay, well, the tall 30, 60, 90 triangle, it's not memorized. You just understand that the side lengths are either root 3 over 2 or a half. Root 3 over 2 is bigger than 1/2. This is root 3 over 2. This is a half. What's the sine of 60 degrees? You should know. You should be able to do it. Okay, 30, 60, 90. Here's what all my 30, 60, 90 triangle ratios have to be. Sine over hypotenuse has to be root 3 over 2. Cosine over hypotenuse has to be a half for any size 30 to 60, 90 triangle. Tangent, root 3 over 2 divided by a half is just root 3. It's root 3 over 2 times 2 over 1. Dividing is the same as multiplying by the reciprocal. Cosecant, 2 over root 3 simplifies to be 2 root 3 over 3 after multiplying the top and bottom by root 3. Secant, cotangent, flip root 3, rationalize. Got it? Great. Random like side question is like slope of a terminal ray. So it's like, hey, what's the slope of this line segment, this terminal ray? What's the slope of this terminal ray? What's the slope of this terminal ray? It's actually no big deal if you understand your 30, 60, 90 and your 45, 90 triangles. If you got pi over 3, you understand 60 degree reference angle created. I'm not going to draw the circle, but I'm going to pretend that we have it doesn't matter. I know one circle. I know one triangle that has a 30, 60, 90 angles. Its hypotenuse is 1. I know that triangle. What's the slope of this? Well, the slope is a rise over run. That's the y distance divided by the x distance. The rise is the y. The run is the x. Boom, I've just found slope. It's like something that's designed to maybe trick you by the way it's asked, but it's not supposed to be tricky. It ends up being the tangent of the value. Pi over 4, if I have an hypotenuse of 1, and I understand pi over 4 is 45 degrees with reference, we got root 2 over 2 over root 2 over 2. That's the rise over run. That's the slope of 1. Pi Pi over 6, 30 degrees. We have to keep this in our brains. It has to be memorized. / known. Hypotenuse of 1, short side, longer side. The rise over the run is 1/2 divided by root 3 over 2, which is 1 over root 3, which is root 3 over 3. This is a great one. Theta equals tan inverse of 4/7, and you're probably like, what? Well, it's like, let's rewrite this. Maybe by taking the tangent of both sides to see the tangent of theta equals 4/7. If I have a triangle with some angle measurement theta, that's not given to me, but I know that the tangent of theta, the ratio that has to exist for this angle, is 4/7. I know the opposite has to be 4. The adjacent has to be 7. Oh, I get it. This terminal side of this angle, which I don't know, I know what the slope is. It's got to be opposite over adjacent or rise over run, which is just 4/7. Cool. All right. This is serious stuff, guys. If you're breezing through any homework, make sure it's not this one and the next one, okay? Or else the rest of the year is going to be tough for you. Hope you get it. We'll see. Mr. Messer, out. I want you to see my email. Later.